All right, so as far back as you go in time, humanity has always had the desire to explore. First on land, then out in the sea. But what's next? Thanks to early explorers, there's little more to discover on our planet, which prompts us to look up. The potential of space is unknown. We simply don't know what lies above, and that's what makes space so exciting. But due to our current forms of technology, we can't find out. We can't learn, we can't explore, and we can't grow. So how do we fix this? Well, we tackle the problem at its source. The main fork in the road for exploring space is propulsion. Frankly, our means of transportation in space aren't going to cut it if we want to go to Mars, let alone interstellar space. For starters, chemical propulsion is too slow. The fastest chemical rocket only goes 36,000 miles per hour, which is not very fast. With that speed, a round trip to Mars is over a year. Aside from that, they take up way too much fuel since they require an added oxidizer, which drives the price up a lot, making a trip to Mars anywhere between $100 to $500 billion. How do we fix this? Well, I present to you Alta Space Technologies. Here, we're working to create a more fuel-efficient form of propulsion to take us beyond the horizons of Earth. Combining antimatter propulsion, laser particle accelerators, and nuclear thermal propulsion, we can create a spacecraft capable of reaching the depths of space quicker and more efficient than ever before. Our tech will be sent to space in a second stage capsule with an onboard thermal antimatter propulsion system or positron reactor. Now, that was a lot, so let's break it down. Our capsule will be flown to space with normal rockets, and from there, our tech can go into effect. As opposed to traditional fuel, we use antimatter. What is that? Well, essentially, antimatter is the same as normal matter, and we all know what normal matter is. Solid, liquid, gas. I'm matter, you're matter, everything is matter. What makes antimatter so special is that it's virtually identical to normal matter, except their charge and spin are reversed. Since the electron has a negative charge, its counterpart would have a positive charge. That's why it's called a positron. On our spacecraft, we turn electrons into anti-electrons or positrons. And we plan to make these directly in the vacuum of space because on Earth, we need a particle accelerator, which is insanely expensive. Now, going into more depth, when a particle and its counterpart come in contact with each other, they're converted into pure energy. This is known as annihilation. Our spacecraft relies on annihilation to heat our liquid hydrogen propellant, which rapidly expands and exits through the nozzle in the back to produce thrust. At the front of the capsule, we have a high-powered laser that's directed at a sheet of gold, which serves as a catalyst for creating positrons. In nanosecond-long pulses, our laser will irradiate the gold, causing all of the atoms to speed up really, really fast until finally their electrons break free. As electrons travel through the sheet, they interact with the nuclei of the gold and turn into positrons. These positrons are then directed with electromagnets to the back of the capsule, where they attract and collide with matter, causing that annihilation I talked about earlier. Once in contact with each other, they're converted into pure energy. This whole process of annihilation produces a large amount of heat and light, which heats the fuel and propels us into space. With just one pulse of this laser, 100 billion particles of antimatter are produced, and since only 10 milligrams are needed for a trip like Mars, we really only need a few shots of this. And with this tech, we can reach speeds up to 180,000 miles per hour. So that trip to Mars I was talking about, it's looking to be as little as 1 month as opposed to over a year. Regarding cost, by using thermal antimatter, that same trip could be cut down by more than 80% compared to traditional fuel. In total, this project would be around $50 million. The laser is approximately 500,000. The electromagnet system for guiding antimatter is an additional 2 million, and the reactor system for heating propellant is another 25 million. So, as you can tell, making rocket engines isn't very cheap, but as we continue to progress, in the next 5 years, we'll be seeing a high return on investment in the space market, registering a CAGR of 8%. By 2030, the global space industry will be worth 600 billion, and by 2040, 1 trillion. We plan on licensing our tech to space agencies like NASA and the ESA, since they're the most capable of producing and affording it. We plan to have a 5-year licensing plan costing around 100 million, but pricing is expected to increase as our engine becomes more widely used. We predict that in the next few years, after research and development, our capsules could be ready for use as early as 2034. For more information, please refer to our website where you can find a more in-depth analysis of our cost and technology. With just twice the fuel efficiency of current rocket engines and potentially 1/5 of the cost, thermal antimatter propulsion is the future of space travel. With our technology, the limits are boundless. Our exploration is no longer limited to the confines of Earth. So yes, we don't currently know what lies above, but with the help of our spacecraft, we can explore, and we will explore by enabling humanity to go farther, faster.